Let's continue our discussion of generating functions. So we want to look at properties of generating functions. And we are going to be specifically interested in non-negative random variables. And generating functions are only defined for discrete random variables. So we are interested in the random variables which are related to the population size and their generation, and that can't be negative. So let's consider in general, X is a random variable taking values in the non-negative integers. And Gx of u is going to be the expectation of u to the x. And this is the sum k equals naught to infinity u to the k times the probability that x equals k. In general, the sum should go from minus infinity to infinity, but we have a non-negative random variable, so it only goes from naught to infinity. Okay, so couple of properties. So what can we say about Gx of 1? If we set u equals 1, then u to the k is also 1 for all k. And this just becomes the sum k equals naught to infinity, the probability x equals k. And then this is 1. It's the sum of all possible, sum over all possible values k, the probability that x takes the value k, and so by the law of total probability, this is 1. And in fact, this is true even if x, for this we don't need the random variable x to be non-negative. True even if x can be negative. So for any random variable, the generating function evaluated at 1 is 1. Okay, so the second property is only true for non-negative random variables, and this says that Gx is increasing. It's an increasing function. So if u increases, then so does Gx of u. And okay, so this is easy to see. Gx is a sum of, so it's 1 times the probability x equals 0. The constant 1 is a non-decreasing function. By increasing function, I just mean non-decreasing. The constant function 1 is non-decreasing. Then u is an increasing function, u squared is an increasing function, u cubed is an increasing function, and so on. So Gx of u is a sum of increasing functions with non-negative coefficients. So it's either increasing or at least a non-decreasing function. Okay, it could be constant. It could be that x takes the value 0 with probability 1, in which case Gx of u is the function which is identically 1. It's the constant function 1. So that could happen, but other than that, it's in fact an increasing function. And this does require, this uses the fact that X is non-negative. Because 1 over u squared, and so on are decreasing functions. And if they had positive coefficients, then you are adding increasing and decreasing functions. And it's not obvious what it's going to be. And then the last property we are going to use is that Gx is convex. And again, this is because just looking at the power series expansion, it is a sum. This again, okay, you can show this, right? This is true even if X is non-negative. And sorry, true even if X can be negative. And the reason Gx is convex is that it's a sum of convex functions with non-negative coefficients. So u to the k for any k is a convex function. Whether k is positive or negative, u to the k is convex. And then we are taking a linear combination of, or we are taking a convex combination of convex functions. Okay, fine. We are taking a combination of convex functions with non-negative coefficients. That's all we need. That these coefficients add up to 1 is not important. They are non-negative, and so the sum is convex. Okay, the reason for this is that this is a sum of convex functions with non-negative coefficients. And these properties are going to be relevant to the picture I'm going to draw in a moment. And I hope these properties are clear. We'll need one more property. So let's look at G. So again, let's focus on. So let's start with the definition of a generating function. So Gxu is the sum k equals not to infinity u to the k probability x equals k. So this is a power series. And the probability that x equals k is, for different k, is a collection of numbers that adds up to 1. So sum k equals not to infinity of this is 1. So the sum of the coefficients in the power series can be added up. They add up to something finite. So if you think of, now we've so far mainly thought of u as a real number, but now let's think of it as a complex number. So the function gx can be defined on the complex plane. And it is a convergent power series on the unit disk in the complex plane. So it's a convergent power series on the set of u complex numbers u such that the absolute value of u, the modulus of u, is less than or equal to 1. Okay, so if we draw the circle of unit radius and the complex plane, then everywhere within the circle, the sum is well defined. We can add it up. Outside the unit circle, the sum could blow up. It could be on the real line, it could be plus infinity. Outside the real line, it could be undefined because it involves canceling infinities. But at least inside and on the unit circle, it's well defined. And it's a known fact that if you have a power series, then you can differentiate this term by term, and that's convergent inside its circle of convergence. Okay, so therefore, the derivative gx prime u is well defined within the unit circle. Okay, so it's well defined inside the unit disk. And in particular, restricting ourselves again to the real numbers, it's well defined between on the open interval -1 to 1. It may or may not be well defined at 1, and you'll see examples in your homework problems where it is well defined at 1 and where it isn't. And that's what's going to be of interest to us. But I just wanted to mention that you can, inside here, it's perfectly okay to differentiate it, and you can do so term by term. So you can switch the order of differentiation. In the sum, you can switch the order of summation and differentiation inside the unit disk. So let's do that. Okay, so gxu was the sum, k equals 0 to infinity, u to the k probability, x equals k. And so if we differentiate this gx prime u, we can switch the order of summation and differentiation. So we get the sum k equals 0 to infinity, the probability that x equals k, times the derivative of u to the k, which is, and now I should switch this. So this sum now goes not to infinity, but 1 to infinity. Okay, so the term corresponding to 0 has u to the 0, which is a constant. When you differentiate it, that gives you 0. It's only the other terms in the sum from 1 to infinity, which give you a non-zero derivative. And the derivative of u to the k is k u to the k minus 1. Okay, and this formula is valid for all u between -1 and 1. It may be valid outside this interval, but we know for sure that it's valid inside this interval. And so let's take the limit as u increases to 1 of gx prime u. As u increases to 1, u to the k or k minus 1 increases to 1. And so this limit is just the sum k equals 1 to infinity, k times the probability that x equals k. But you know what this sum is. You recognize this as just the definition of the expectation of the random variable x. Okay, so we can calculate the mean of a random variable by differentiating its generating function at 1. And that should be understood more carefully as taking the limit as u increasing to 1 of these derivatives. Usually the generating function is differentiable at 1 and the limit is the same as gx prime 1. But even if gx is not differentiable at 1, you can calculate this expectation by taking the limit. Okay. This limit will exist if x is a non-negative random variable. Otherwise, the limit may not exist and the expectation may be undefined. But for a non-negative random variable, the expectation is always well defined, but it could be infinity. Okay. So this expectation is well defined because x is non-negative. But it could be plus infinity. An expectation becomes undefined if it's of the form infinity minus infinity, which cannot be computed. And that can happen only if a random variable has probability of taking both positive and negative values. Okay, good. That was a long aside on generating functions. And that's just to justify the picture I'm going to draw now. And let's remind ourselves again why we are doing all this. We are doing all this because the probability that Zn, the population size in the nth generation of a branching process, the probability that that takes the value 0 is the same as the generating function of the offspring distribution composed with itself n minus 1 times evaluated at 0. Okay, so this is what we want to calculate, or more precisely, we want to calculate the limit of the left-hand side as n goes to infinity. Okay, and let me tell you what that limit is. So let me pause here again. I might come